The special theory of relativity, which we will just call relativity, takes into account the fact that the speed of light in vacuum is a physical constant. This theory was introduced in 1905 by Albert Einstein, based on two postulates. First postulate: the laws of physics are the same in every inertial frame of reference, also called the principle of relativity or the relativity principle. The second postulate is that the speed of light in vacuum is the same in all inertial frames of reference and is independent of the motion of the source. Recall that the speed of light c is equal to 3 times 10 to the 8 meters per second. These two postulates have some surprising results, even for the simple case of motion at constant velocity. An inertial frame is one in which Newton's first and second laws are valid. Recall that a frame of reference, or a reference frame, is conventionally a system of space coordinates x, y, and z, with axes at right angles to each other that intersect at an origin, plus a time coordinate t, also with an origin at t equals 0. Let's give this frame the label S. Thus, in frame S, an event E is represented by a point in time and space with coordinates t, x, y, and z. Motion of an object is measured relative to a frame, in which the object has a position vector r, a velocity v equals dr dt, and an acceleration vector a equals dv dt. In an inertial frame, Newton's first law is valid, so an object has a constant velocity in that frame, whether v equals 0 or v is non-zero, unless acted upon by a net force F net. The first law is also called the Law of Inertia. Also, Newton's second law, F net equals ma, where m is the mass of the object, is valid in an inertial frame. If there is no net force, there is no acceleration, and if there is no acceleration, there is no net force. Note that a force is due to a physical interaction with other objects, such as gravity or electromagnetism. If there is no such physical interaction, there is no force, and hence no acceleration in an inertial frame. An accelerating frame is non-inertial. Consider an object at rest or with constant velocity in an inertial frame S. This object has no net force acting on it. Then, in a second frame S' that is accelerating relative to S, this object accelerates in the opposite direction. But there is no net force acting on it, so Newton's first two laws are not valid in the accelerating frame S'. On the other hand, suppose that in S the same object has the same acceleration as the accelerating frame S'. This means that a net force acts on the object. In the accelerating frame, the object has zero acceleration, so the object has constant velocity. And once again, Newton's first two laws are not valid in the accelerating frame, so an accelerating frame is not an inertial frame. If, measured in a first frame that is inertial, a second frame that is accelerating is non-inertial, it follows that a second inertial frame can only move with constant velocity relative to the first inertial frame. Therefore, all inertial frames move with constant velocity relative to each other. Two inertial frames can be in relative motion with a velocity in any direction, and their axes can be in any orientation. Both frames measure the same points, events, and objects in time and space, regardless of how the frames are oriented or moving, and also independently of the units used in each frame. Then numerical values of time and space coordinates may be different, but they measure the same things. For simplicity, we will work with two inertial frames, S and S' in standard configuration. In S', coordinates are t', x', y', z'. At t equals 0 and t' equals 0 in both frames, their origins, O and O', are at the same position, and their axes are aligned with x' along x, y' along y, and z' along z, with positive x' along positive x, and so on. S' moves relative to S with speed u in the x direction, so in S it has velocity u0, 0. At a later time t, O' has moved a distance x equals ut along the x-axis. The x and x' axes are still aligned, but offset by ut, and the y and z axes, though no longer aligned, remain parallel. Note that viewed in S prime, S moves in the negative x prime direction with speed u, so the velocity of S is minus u, 0, 0, measured in S prime. We have encountered a form of relativity before, namely Galilean relativity. Consider frames S and S prime in standard configuration, and let the coordinates transform from S to S prime as follows. So time is the same in both frames, and x and x prime have an offset ut. Transforming the other way from S prime to S, we have x equals x prime plus ut prime. Suppose that you are standing at rest on the street at the origin of S, and a car drives past with speed u. The driver of the car is seated at rest in the car at the origin of S prime. You will measure the driver's position as x equals 0 plus ut equals ut, moving past you at the speed of the car, whereas the driver will measure your position as x prime is equal to 0 minus ut prime, which is equal to minus ut prime, moving backwards with speed u. We can find the velocity transformation between the frames as follows. Consider a particle p with position vector xyz, velocity vx, vy, vz, and acceleration ax, ay, az. Then we proceed as follows. So acceleration in both frames is the same, as expected in inertial frames. The transform Vx equals Vx prime plus u is how we intuitively understand the motion of a projectile launched from a moving source, which is that the projectile gains the motion u of its source, which is added to its own intrinsic motion v prime, to give a greater motion v relative to an outside observer. However, this understanding is inconsistent with Einstein's second postulate, which is why the special theory of relativity has results that are counterintuitive.